Modern air combat is not a simple contest between one aircraft and one missile, nor is it a duel between a single radar and a single target. It is a dense, time-compressed interaction among many sensors, weapons, computers, and human decision-makers, all operating in parallel across air, land, sea, and space. When a fighter aircraft penetrates a hostile airspace to strike a target, it is simultaneously an attacker, a sensor node, a potential target, a participant in a much longer network. Understanding how such an aircraft survives and fights in an environment filled with enemy fighters, surface-to-air missiles, cruise missiles, and layered radar coverage requires abandoning the idea of one radar tracking everything, instead appreciating the logic of distributed sensing, layered defense, and sensor fusions. At the heart of a modern warfare lies the fact that no single sensor can do everything well. And instead appreciating the logic of distributed sensing, layered defense, and sensor fusion. At the heart of modern air warfare lies the fact that no single sensor can do everything well. Radar physics imposes unavoidable trade-offs. Long wavelength radars can see far, are relatively restrained to weather and some forms of stealth shaping, and they offer poorer resolution. Strong wavelength radar provide precise tracking and discrimination, but suffer from limited range and greater sensitivity to clutter and atmospheric effects. Ground-based radar are powerful and persistent but constrained by the curvature of the Earth, which limits their ability to see low-flying targets. Airborne radars can look down and extend coverage but are limited in size, power, and cooling. But what an aircraft can carry. Space-based sensors can provide global awareness but often lack the resolution and update rate required for tactical engagements. Modern air defense and air combat emerge from combining all these effects, sensors into a coherent whole. When a fighter aircraft such as an F-16 Sukhoi 30 and Rafale enters contested airspace, it carries its own radar optimized for tactical use. This radar is designed to detect and track airborne targets within a forward sector. Support beyond visual range engagements, map the ground for navigation or targeting, and maintain situational awareness in fast-changing conditions. It can track multiple targets at once using track while scan modes, but its range and field of regard are limited by the size of its antenna and the power available on board. Crucially, this radar is not expected to replace the whole of strategic warning radars or wide area surveillance systems. Instead, it is one sensor among many in a large ecosystem. Ground-based air defense systems are built on different philosophy. Systems such as the Akash, S-400 or S-500 are not single weapons, but families of radars, launchers, and command posts, as well as data links. A long-range acquisition radar scans vast volume of airspace to detect potential threats at great distances. Once a contact is detected, shorter range or high resolution radars refine the track, classify the object, and provide precise data for engagement. Fire control radars then illuminate or guide interceptors towards their targets, while command and control systems manage priorities, prevent duplicate engagements, coordinate with other units. Each radar performs a specific function. The system's strength lies in how these functions are orchestrated. Airborne early warning and control aircraft play a critical bridging role between airborne fighters and ground-based defenses. Flying at high altitude with powerful radars, they can see hundreds of kilometers in all directions, often beyond the radar horizon of ground systems. They provide early warning of enemy aircraft, cue fighters towards threats, and relay information between different elements of the force. In many scenarios, an AWACS aircraft will detect an incoming fighter or missile long before a frontline fighter's own radar can, allowing the fighter to remain passive or focus its sensors elsewhere. This shared awareness dramatically increases survivability and effectiveness. The challenge becomes even more complex when different categories of threats appear simultaneously, as an aircraft may face many enemy fighters, launching air-to-air missiles from behind, surface-to-air missiles rising from ground batteries, and cruise missiles approaching at low altitude from ships or coastal launches. Each of these traits behave differently, presents a different radar signature, and demands a different response. A high altitude, long range missile can be detected early by strategic radars and engaged far off its target. A low flying cruise missile can remain invisible until it crests the radar horizon, leaving only seconds for reaction. A fighter launcher missile may be guided initially by the launch aircraft's radar, then transition to its own seeker in the terminal phase. No single sensor can optimally detect and track all of this at once. And why is this? And which is why layered systems exist. Radar band diversity is central to its layering. Lower frequency radars are often used for wide area surveillance and early warning. They can detect objects at long ranges and are less effective by some stealth techniques. Though they may struggle to precisely locate or classify small low-flying targets, higher frequency radar provides the accuracy required for weapons guidance, discrimination, but operate over shorter ranges. By combining data from multiple bands, a defense network can achieve both reach and precision. A long-range radar may be first to alert the system to an inbound threat, with a high-frequency radar refines the track and supports interception. The aircraft itself continues with its onboard radar and passive sensors, filling gaps and adding perspective. Passive sensors are as important as active sensors in the environment. Radar warning receivers detect hostile radar emissions and provide early cues that an aircraft is being searched for, tracked, or targeted. Electronic support measures can identify emitters by their unique signatures, offering clues about the type of system involved. Infrared sensors can detect the heat signature of aircraft and missile plumes without emitting energy, making them harder to counter. Missile approach warning systems which watch for the characteristic signature of coming missiles and trigger defensive responses. These passive systems complement radar by providing information even when radar use is limited or denied. All of this information flows into battle management and emission computers that perform sensors fusion. Sensor fusion is not simply displaying multiple tracks on a screen, it is the process of correlating reports from different sensors, determining which detections ref- refer to the same object, filtering noise and false alarms, and producing a coherent track with estimated position, velocity, and identity. This fusions picture allows both humans and automated systems to make decisions quickly. It's the fusion engine, rather than any single radar, that enables simultaneous tracking of many threats of different types. In a real engagement, timelines differ dramatically depending on the threat. A high-altitude ballistic or hypersonic threat may be detected minutes in advance, allowing long-range interceptors to be launched well before the threat approaches defended airspace. A cruise missile hugging the sea may appear only tens of kilometers away, requiring rapid engagement by short-range systems or point defenses. An air-to-air missile launch from a nearby fighter may give only seconds of warning, forcing the target aircraft to rely on onboard defensive aids such as electronic countermeasures, decoys, aggressive maneuvering. The defense network must handle all these timelines at once, allocating sensors and shooters accordingly. From the perspective of a fighter pilot, the complexity is most hidden between interfaces designed to reduce cognitive load. The aircraft's defensive aids use integrated warnings, countermeasures, and displays so that pilots doesn't have to interpret raw sensor data when a missile is detected. The system may automatically deploy flares or shafts, active jamming, or cue directional infrared countermeasures. At the same time, the pilot is not passively waiting to be attacked, it is actively participating in the information war. Cruise missiles add a particular challenge because of their low altitude and small radar cross section. Their designers exploit the limit of radar horizon and ground clutter, flying routes that minimize detection until the last moment. Defending against them requires sensor coverage, including coastal radars, shipborne radars, airborne platforms, and sometimes even passive detection networks. Once detected, engagement often falls to short-range systems with high reaction speed rather than the long-range missile optimized for aircraft or ballistic targets. Again, the key is that system assigns the right sensor and interceptor to the right threat at the right time. Long-range surface-to-air missiles such as the S-400 and 500 illustrate the layered approach particularly well. Those systems are designed to counter a wide spectrum of targets, from aircraft to cruise missile to ballistic threats, but they do not rely on a singular leader or interceptor. Multiple radars operate in different bands, each optimized for a particular role. Different missiles within the system are tailored for different ranges and target types. Command elements decide which interceptor to use against the target. Based on speed, altitude, trajectory, and threat priority, the system's ability to track many objects simultaneously comes from distributing tasks across its component, not from overloading one radar. It is important to understand that tracking doesn't always mean continuous illumination or observation by one sensor. Track files are predictions as much as observations, updated whenever new data becomes available. A target may be detected by one radar, then temporarily lost behind terrain, then reacquired by another sensor. The battle management system maintains continuity by predicting motion, correlating new detection while existing tracks. This allows the network to track more objects than any individual sensor could observe at time. The offensive side of the equation mirrors this complexity. When a fighter launches a missile, that missile may rely initially on data from a launching aircraft or another sensor to the network. Mid-course updates may be provided by the AWACS or ground radar rather than the shooter itself. In the terminal phase, the missile's own seeker takes over. This shared responsibility allows shooters to disengage, maneuver defensively, or even turn away while missile continues its targets. Offense like defense is a network activity. The idea of radar bands as strictly short, medium, or long range can be misleading. It can, if taken too literally. While frequency influences range and resolutions, real systems are defined more by the role than by the simple band labels. A radar may operate in multiple modes, trading ranges for resolution, or vice versa, depending on task. Modern electronically scanned arrays can shift beams rapidly, dwell longer on areas of interest, and adapt waveforms to the environment. This flexibility allows a single radar to continue and contribute to multiple roles without being the single role solution. In scenarios involving multiple simultaneous threats, prioritizing becomes critical. No defense system has infinite interceptions or unlimited processing powers. The battle management system evaluates which threats pose the greatest danger, which can be engaged earliest, and which requires immediate action. A high speed missile headed directly for a critical asset may take precedence over a distant aircraft on an ambiguous trajectory. Fighters may be tasked to intercept enemy aircraft before they can launch, while ground systems focus on inbound missiles. The division of labor is dynamic and can change within seconds as the solution evolves. The human decision makers remain central despite high levels of automation. Operators and pilots interpret the fused picture, apply rules of engagement, make judgments about intent and priority. Automation accelerates detection and response, but humans provide context and restraint. The effectiveness of a defense network depends not only on technology but also on training, doctrine, coordination among units. A well integrated but poorly trained force may perform worse than a simple system operated skillfully. Electronic warfare further complicates radar tracking, jamming, deception, and emission control can degrade sensor performance and can create false tracks. Modern systems are designed to operate in contested electromagnetic environments using techniques such as frequency, agility, passive sensing, cross cueing between sensors, and maintain awareness. Even so, electronic warfare can reduce detection ranges and increase uncertainty, reinforcing the need for redundancy and layered coverage. In this context, survivability is not invulnerability about managing probabilities. Each layer of detection, each sensor, and each countermeasure reduces the chance that a threat will succeed. No aircraft or system can guarantee survival against these threats, but a well designed network can make attacks costly, complex, uncertain for the adversary. The interaction of offense and defense becomes a contest of systems rather than isolated weapons. Ultimately, the question of how one radar can track BrahMos, an Akash interceptor, a Meteor missile, and a long-range SAM at the same time is answered by rejecting the premise. It is not one radar doing all the work. It is a web of radar, sensor, data links, computers, and people, each contributing a piece to the picture. The fighter's radar, the ground battery's acquisition radar, the fire control radar, the AWACS platform, the passive sensors all see different aspects of the battlefield. Their data is fused, prioritized, and acted upon in parallel. Modern air warfare is therefore less about individual platform, more about integration. The aircraft, the missile, the radar are no longer standalone entities, but nodes in a complex system. Success depends on how well these nodes share information, how intelligently they allocate tasks, how quickly they adapt to change. In an environment, simultaneous threats are not an anomaly, but the expected condition and ability to manage them is the defining feature of contemporary air power.